the new video again. In this video, we are going to discuss scope of quantifiers. Scope of quantifiers. So, so what is scope? So quantifiers, we have two quantifiers. One is existential and second is universal. Okay. So, so we will understand with some example. Let's say there exists some x and px and qx. These are predicate functions, alright? Predicate functions. So for which x, for which predicate function this x is valid. So what is the scope of this? So this is equivalent to px and is equivalent to py. So qy. So this x and this x and this x is different, alright? This is one. This is a scope for this x. This is different here. So this is equivalent to like that, right? And same as for all x px implies qx is also equivalent to for all x px implies qy. Alright. So these are operators, alright. These are operators. So what we can say, scope of quantifier can't exceed operators. This would be a one note here. Second is, we can say here this x is bounded variable and this x is free variable, right? So one note more, to eliminate ambiguity we can use braces, or we can say parentheses. Alright. So for exposing both the variables to quantifier, we can use like this, px and qx. They both are bounded variables here, right? So next we will discuss nested quantifiers. What is nested quantifier? Nested quantifiers is like uh, more than one, more than one quantifier fire in one expression, or we can say with one predicate logic. So first example would be like for all x and for all y, predicate logic px comma y, right? There exists some x for all y for which px comma y is true. How we read this? There exists some x for all y's where px comma y is true, right? So Number 3 would be like this: for all x, there exists some y for which px comma y is true. 4 is there exists some x for all y x, and there exists some y for which there is some x for some y for which px comma y is true, right? So how we say it? Uh, for all x is there exists some y for which px comma y holds true. So that's how we read this. And next would be गणेश, कल तू प्रिंट निकाल के लाने जरूर, मैं तो भेज दूंगा वो भी, ठीक है? Holds true. Next will be for all y, there exists some x for which px comma y is true. Right. Now we will solve some examples here. What is this? Next is this line. Next is right. Right. This thing I discovered new. So all right. For example, let's say there is a predicate function. Right. Predicate function px comma y here, like x is greater than y, right? And x comma y belongs to 1 comma 2 comma 3. It's a finite domain, right? First will be like that: for all x, for all y, is px comma y is true. Is this statement true or false? So we can say that, let's say there is x should be greater than y always for all x and y. But this is not. Let's say y is equal to 2 and x is equal to 1 and x is uh, greater than y does not hold. This is false. Alright. For all work as we will discuss it further. Next example. And next we will find for this is question for all x there exists some y for which px comma y is true. So for all x there exists some y. So x is what, like, for all x there exists some y. Is y 1 comma 1 or 1 comma 2 or 1 comma 3 for all x. There exists some y for all x where x is 1 here. Now x is 2 here. 2 comma 1, 2 comma 2 or 2 comma 3. So this is false. False and anything is false. That doesn't hold also. Right. So for all predicate logic like that. For all x means x1 and x2 and x3 dot 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 and xn. The rejection x means x1 or x2 or x3 dot 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 xn. This is like that. So it's true. Next example is like that. Px is equal to x plus y is equal to 10 and domain is set of integers. Right. So what is true and what is for all x, for all y, px comma y holds true. So what we are saying here is, so in this what we are doing is, Alright guys, so in this what we are doing here is for all x and for all y, px comma y is true or not. So for all x is, let's say uh, x is equal to 1, alright. So 1 comma 2 p of and p of 1 comma 3 1 comma 9 is equal to 10. No, so this is false, so entire is false. Alright, next would be, right, so next is, there is some x and there is just some y for which px comma y is true. So there exists some x and there exists some y for which px comma y is true. So this is correct, I think. Let's say x is 1, there exists some y for this is 9, there is minus 1, this is 11. So this is correct, right? Next would be like, uh, for all x there exists some y. For all x there exists some y for which px comma y is true. So I think this is also true here, because for all x, we say x value as 1, comma 2 and 3, 4 and 5 and so on. There's some y also for 1, 8, 7, 6, 5 and so on. So this is also true. And there exists some x for all y for which px comma y is true. Is this correct? Let's see. Px of x, there exists some, let's say that x is 9, which is correct for all y's, which is wrong. Alright, so we are not doing this like that. There is at least x for which all y we get px comma y. This is wrong, right? And next example is similar like this. Alright, this is hanging now. Alright, next example is p of x comma y comma z is equal to x plus y plus z is equal to 10. So let's say first is, for all x there exists some y and there exists some z for which px comma y comma z is true. To solve these type of questions, we can go for this. Let's say y and z are their existential form. So we keep them right here. Y plus z is equal to 10 minus x. So for all x, let's say x has values 1, 2, 3, and 4. We can find some y and z for which this is true. Let's say x is 4. 4 equals 6, x y plus z 2 plus 3. So this is correct, I think, yes. And next is, there exists some x for all y and for all z for which p x comma y comma z is true. So we can do this like that: x is equal to 10 minus y minus z, and yz can contain any value. So this result is always integer. Alright, so it can fulfill by x always. So this is also true. Third is there any x which is equal to like this? No, this is false here. Not possible. Next Alright, welcome back guys. And next example is there exists some x for all y for which x plus y is equal to 1 to 1 plus y. Right? So x is equal to 1 to 1 plus y minus y equal to 1 to 1, which is not integer. Not integer. This is false. Right? Fourth question is like there exists some x for all y for which x plus y is equal to 2 plus y to 2 plus y. X is equal to 2 plus y minus y, which is 2, which is integer. This is true. Negating quantifiers. So what are negative quantifiers? Let's see. Negative point five is like there is negation of for all x. Px is like px1 and px2 and dot dot pxn complement, which is like px1 or px2 or px3 dot dot pxn complement. Similar is like that, right? Uh, there exists some x px would be like negation of p1 px1 or px2 or dot 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 pxn, which is like alright. So guys, that would be like px1 and px2 complements like that. Next topic is properties of quantifiers. Then we will do some questions. We will do translation. After translation, we will check the right. So next is properties and quantifiers. We have 15 minutes remaining in the lecture. You can do these things also. So properties of quantifiers. So first property is for all x, px implies there exists some x, px. Right. Second is for all x and for all y, pxy implies equivalent to for all y, for all x, px comma y. Right. Third will be alright. Third is there exists some x and there exists some y, pxy is equivalent to there exists some y and there exists some x, pxy. Right. Fourth would be like there exists some x for all y, pxy implies for all y there exists some x, px comma y, for which px comma y is true. Fifth is for all x, px of and qx is equivalent to there exists some x, px or there exists some x, qx. Right. Six would be for all x, px and qx. It is equivalent to for all x, px, for all x, qx. Note is one note is Notice for all is not distributive over disjunction. Alright. For all x, for example, is that for all x, px or qx is not old. There exists for all x px or for all x qx. Alright. Now seventh number is there exists some x for which px implies qx, which is this implies for all x px there exists some x for px which px implies for all x some x qx. We can replace this with for all, right? And next is for all x px implies qx implies for all x px implies for all x qx. If number 10 is there exists some x px implies qx, reverse direction in here. There exists some x px implies there exists some x qx. So is this not right for that? There's reverse direction only. Alright, this is not my lord. Right. Next note would be like 11 is there exists some x for which px or q, right, which is equivalent to some x px or q and q. Alright. Next is p1 k plus q. Q equal p1 dot p2 complement plus q. This does not hold here. Universal quantifier is not distributed over disjunction in discrete mathematics. According to schema, the universal quantifier denoted by for all does not distribute over This means that such statement for all x px or qx into for all x qx or for all x is original for this is that the first statement claims that for every element in domain at least one of the predicates px or qx is true. Right. Not logically equivalent to q. Right. Since we are trying to discuss the last yes statement is true in empirical logic. Both x-rays indicates that if q allows for every x, if px is true, then q is true. Allows for some x where px is false. second statement, if x is true for every x, then which is stronger claim because it's before making any claim about q. Right. So is not only. So this says for all x, if px is true, then q is also true. And this says if px is true for all x, then q is true. Logically stronger than LHS. Stronger than LHS. Right. Yeah. Next, we will do some questions and then translation. Thank you so much, guys, for watching the lecture. And next, we will practice some questions. Next lecture. Hope you understand the meaning. Thank you, guys.